Okay, in this video I want to show you how to calculate the pH of an aqueous solution of some salt. And what I had in mind was this. Let's calculate the pH of 0.35 molar Kf, potassium fluoride. And we might want to ask the question, well, why does that even have a pH? I mean, this is something you should always ask. Why does that have a pH? In other words, well, why isn't it neutral? And so let's look at the individual ions here. We have a potassium ion, and the potassium ion has no reaction in water, and so it's we might say there's no reaction. In other words, there's no reaction that produces acid or base. And then we have the F- ion, the fluoride ion. As you know, Kf is ionic and is therefore completely dissociated. So we've got fluoride ions running around in this solution. Would they have any effect? Would that produce an acidic or basic reaction? And the answer is it would be basic. And a good way to remember this is that fluoride is the anion of a weak acid. I mean, you do have to know what your strong and weak acids are. Most acids are weak, and so this is basic because it's the anion of HF, and HF is known to be a weak acid. I mean, if an acid is weak, doesn't it make sense that its conjugate base must be fairly strong? And so that's what makes it a weak acid, because the conjugate base, in this case F-, is holding on to that H fairly strongly. Okay, so F- then is basic. The next question we might ask is, well, if it's basic, what does that mean? It means it produces hydroxide. So then we could say, well, what's the equation for that? How would you get hydroxide ion? And so we'll write out this equation. F- is going to react, I guess I should put aqueous there, plus H2O, liquid, is an equilibrium, and you get HF and OH-. So we are producing hydroxide. So now we'd like to do our mathematical calculation, and we can use what we call an ice, well, some people call it an ice chart. I call it an ice box. It just helps me remember it better. How about you? Ice box. So then we're going to draw these three rows, and we're going to draw three columns. One for fluoride, one for HF, one for OH-. We're going to neglect water because it doesn't, its concentration essentially is constant, because this is an aqueous solution. So we'll put ICE, hence ice. I for initial, C for change, E for equilibrium. The initial concentration then is 0.35 molar for fluoride. Because this dissociates completely, then the fluoride will be 0.35 molar. At some frozen instant in time initially, these are both zero, and then we can imagine that some unknown amount x dissociates of this fluoride, and you're going to produce x of this and x of this, because the stoichiometry is 1 to 1 to 1. So at equilibrium, we're going to have 0.35 minus x. This will be x, and this is x, because there wasn't any to start with, so the change was x, so the concentrations are x. Well, if we knew the equilibrium constant for this reaction, we could calculate what x is. You need either a Ka or a Kb. Well, A stands for acid, B stands for base, so I think we're going to need a Kb. But the thing is, you're not going to find a Kb for fluoride ion in most tables. But you can find a Ka for HF. And so the Ka for HF, we can look this up, and it's 6.8 times 10 to the negative 4. There's a relationship between Ka and Kb. In other words, the acid dissociation constant of an acid and the base dissociation constant of its conjugate base. So Ka times Kb is equal to 10 to the negative 14. So in this case, we can work out that Kb for the fluoride ion is going to equal 10 to the negative 14 divided by 6.8 times 10 to the negative 4. And let me get my calculator here and we'll find out what that is. So on this calculator I've got to put 1 EE plus minus key 14, so that's 1 times 10 to the negative 14. I always like to say that EE stands for times 10 to the. Trust me, it works. Times 10 to the. And then you divide by 6.8 times 10 to the plus minus key 4, and you get 1.47. I guess we could call that 1.5. 1.5 times 10 to the negative 11. Okay, so we'll write that by definition of an equilibrium constant, isn't that going to equal the product of the products, if you will, divided by the reactant? So that's x squared over 0.35 minus x. Well, this often works out to be a quadratic equation. We're probably not going to need one. Let's find out what x would be if we did an approximation. In other words, this is the approximation where we say, well, 1.5 times 10 to the negative 11 is approximately equal to x squared over 0.35. And x comes to, if we do that, it would be the square root of 1.5 times 10 to the negative 11 times 0.35. So, well, let me move this over here. So we could say that x equals, let's see, I'm going to take the, we're going to multiply that by 0.35, take the square root, and change that to scientific notation, and we get 2.3 times 10 to the negative 6. If this passes what we call the 5% rule, then we don't have to do a quadratic equation. Well, I think by inspection you can see that 2.3 times, well, I'll write it out here, but 2.3 times 10 to the negative 6 divided by 0.35 times 100 for percentage, that's way less than 5%, but we can calculate what it is. We'll divide by 0.35, we'll multiply by 100. So this guy is incredibly, I mean, it's only 6 times 10 to the negative 4%. So we'll say that that's just way less than 5%, which means you can keep this as is. The approximation was great. That's all we have to worry about. Now, x is equal to the hydroxide concentration, isn't it? Because we've defined it that way. So if we take the negative log of that, we get the POH. The POH is going to be, so we've got 2.3 negative 6. I'm going to take the log and then just mentally remove that. Well, I can remove it down here. 5.64. So the POH is 5.64. The pH, which is defined as the negative log of the hydronium concentration, H3O plus, or you could say H plus for short, that's going to be 14 minus 5.64. Because remember, pH plus POH is equal to 14. Now that's a pretty important formula. So if we subtract that, and what I'm going to do is just put a minus in front and add 14, which is the same as subtracting it, we get 8.36, or maybe 8, I suppose you could say 8.4. So 8.4 would be the pH of this 0.35 molar KF solution.